for this part of the video itself, if you have not watched the previous two about the change in temperature and change in your state, please watch that first before coming over to this video. Okay, so for this part over here, I want you to notice that there is this diagonal part, the diagonal parts, right? Maybe I should use a different color. Okay, these parts here, the diagonal parts here, right? All diagonal parts here correspond to your change in, okay, maybe I write it. Diagonal refers to the change in temperature. So if it refers to a change in temperature itself, the formula that we use would just be Q equals to MC change theta, or change in temperature itself. Okay. Then whereas for the other one, if you're using the horizontal lines over here, so the horizontal lines itself correspond to your change in state. And if we use a change in state, we will use Q equals to ML instead. Okay, so you can see in the table below itself, do take note, even though you have, like I said in the kinetic particle theory chapter itself, or kinetic particle model of matter chapter, even though solids look as if they are stationary, they are not zero energy, which means even at A or at B, basically you still have internal energy itself. So from A to B itself, you can see is a change in temperature, is a diagonal line. We'll just use MC change theta. So if you want to describe what happens in between them, you can just say that your solid particles vibrate faster in your fixed position. Then for B to C itself, spacing between particles, this one is a bit too short. You might want to describe it in terms of your motion and your arrangement itself, where you will talk about your solids being in your fixed, it can only vibrate about their fixed position, and they're held together in very, very closely packed together itself. And then you can talk about all the different arrangement and movement itself based off the KMM chapter itself. Okay, can you make use of that? So you can actually see this part, the cooling curve and heating curve portion of this chapter is actually very closely linked to your KMM chapter itself. So you need to be very, very proficient in basically all three chapters itself to be actually very good at your thermophysics. So you can just think of the whole entire three chapters of physics as one very, very big chapters, and you have to memorize and perfect them. So a lot of effort have to be really put in to go and memorize all these different chapters itself and linking them together. Okay, now use the space below here. I'm gonna tell you something interesting. Now, how do you know if you have larger specific heat capacity? Basically, we know that you have larger if you have a gentler or flatter gradient. Okay, remember this is for your diagonal. Okay, so if you have a larger specific capacity itself, you actually have a gentler gradient. And if you want to talk about your specific latent heat, which one will have larger? The longer line. Do take note, this is for your horizontals. Okay, now there is a reason why we are talking about in terms of this, so let's explain it. Now we know that for specific heat capacity is small c, right, is Q over M change theta. So if we were to take the change in temperature to be constant, change in T is constant, so basically now we are just comparing Q and specific capacity. We keep the bottom of the denominator constant. So what is Q? Q is energy, right? Remember, energy is basically power times time, where this power comes from the heater. So you can actually see that your time is basically related to Q, which is your E over here, right? So because of this, time is the factor that affects your specific capacity. So the longer it takes for your temperature to increase, the higher your specific capacity. Very complicated, so that's why I'm telling you the simplest way to see whether you have larger or smaller is just to see whether it's gentler or steeper itself. Okay, so this one is more for the derivation that you are not required to know, but if you are curious about why we use flatter means more larger SHC, it actually have to do with the original formula. The same thing also applies if you were to try to use your L equals to Q over M. Same logic, because your Q is also power times time. The longer the time you take, the larger the Q, the larger the Q, the larger the L. Same thing. The more time you take, the larger the E, the larger the Q, the larger the C. So because of this, the longer it is, it takes a larger specific latent heat. You need more energy per unit mass to change state. Okay, so because of this, you need to know. Now, is this necessary to know? Yes, comes out quite often in your school papers. Okay, especially the recent years itself, these have been popping up quite often itself. All right. Now, last and not least, this is the last and final question for this chapter, the word example I mean. So normally the questions won't give you such a crazy question where it's 5 marks. Usually you break it down into smaller pieces. But this one I'm just going to do it as one big whole itself, so it's easier for everyone to see. So, number one, I have all this information and check the units, kg. Now, this part here, if you don't pay attention, you lose marks. Joules per gram. Joules per gram. Okay? Which means you need both masses in terms of your double check. Okay, so mass, we know is 100 grams. We also know that this is 0.100 kg. Okay? Then now, you want to know what's the total energy you need to increase your temperature from -20 to 120, right? First thing, from -20 to 0. Okay? And this one is in terms of degrees Celsius. Okay, so what happens from this? I change temperature of ice. Okay, now all of these steps, you don't have to do it. It's just me telling you, or you should have this in your head. Okay, then from 0, or not from 0, at 0 degrees Celsius, ice melts to form water. Okay, mass constant. Okay, then from 0 degrees Celsius all the way to 100 degrees Celsius, because we are assuming that this is pure water, the change temperature of water. Now you'll notice that later on when I show you the formula itself, why do I need to keep emphasizing is of water, is of ice? All of these matters quite often. Okay, they are very important. Then your water boils to form steam. Okay, don't forget, it's not done yet. Then from 100 degrees C to 120 degrees C, what happens is your steam change temperature of steam. So you can actually see that there's actually 5 steps, 5 formulas. Each and every one of them correspond to one set of formula each. Okay, so if you want, you can actually do it one shot. Okay, but to simplify things and make things clearer itself, I'm going to do it one by one. So first thing, when you actually change from your ice, so from ice itself, you are just changing temperature itself. Okay, the formula is this, and because we're changing the temperature only, we are using specific heat capacity. So of ice is 2100, right? And the gram mass is 0.1. So you just take 0.100 times your 2100. And what's the change in temperature? Change in temperature is 0 minus negative 20, right? So you can just solve using your calculator itself. 0.1 times 2100 times 20, get 4200. And this is joules. Okay, just double check. Yep, okay, so this is for change in temperature of ice. Then after that, we know that ice will melt. So what happens? We know that when you melt ice, it is using fusion, solid to liquid, right? And the mass should be 100 times L, which is 336. So 33600. And and this is in joules as well. Next, change in temperature of water. So I'm just gonna take this formula, so I don't need to write it so many times. Okay, and basically same mass, but now my C is now for liquid water, and your change in temperature is 100 minus 0. So press the calculator itself. 0.1, 4200, 100, you get 42,000 joules. Okay, then Q equals to ml. Your same thing, we're going to use 100 grams again, because now is joules 2260, if I'm not double check, 2260 times 100, yes, 2260 joules. And last but final, Q equals to, and your final one is mass, same thing is 0.100 times, for steam is 2000, and for your temperature is 120 minus 100. Okay, so 0.1 times 2000 times 20, get 4000 joules. Okay, so total heat gain is 4200 plus 33600 plus 42000 plus 22600 plus 4000. This will give you 4200 plus 33600 plus 4200 plus 22600 plus 4000. You have 309,800, and we simplify this into 310,123 joules. Okay, so very long and complicated step, but basically you can see that it corresponds to each and every one. Each step, each stage is all individual. They don't affect one another itself. So if you ever need to draw your temperature time graph, okay, we start from a negative, right? So you start from minus 20, you go here, you have it here, you go here, go here, go here. So 120, 100, you have 0, you have minus 20. Okay, so basically you have each and every one of these, they all correspond to each step, correct, accordingly. This is your temp. This is temperature, and this is time. Okay, so this is how you actually go and calculate it. And if you were to calculate between two objects, heat gain is equals to heat loss. For one object to gain heat, something else must lose heat. So if that's the case, you solve for your total heat gain, and you'll be equals to the total heat loss. Just throw in the formula, ask yourself, always double check. Ask yourself, number one, substance A, does it change state? Does it change temperature? Substance B, does it change state? Does it change temperature? Do you have more than one change state and change temperature? If so, do you need to add them up or whatsoever? Go and double check. Different substances will be on different sides. One will be heat gain, one will be heat loss. You can have multiple heat gains, you can have multiple heat losses. You just need to double check which one is which. Okay? And this is also the reason why, if you notice, right, steam is from 100 to 120 degrees. So which means that if you notice steam, right, steam can be higher than 100 degrees Celsius, but hot water can maximum is only 100, which means in terms of danger itself, steam is more dangerous because steam can lose more heat to you. Okay, you can just as a side note, steam is more dangerous. It's more likely to burn you. Than hot water. Okay, because remember, steam, I will condense first before I change temperature. This is heat loss by steam, and this value is actually equals to the heat gain by person, which means steam can lose more heat to you, whereas for the hot water it is just like this, heat loss by hot water. Okay, so what you can say is that steam has more internal energy, or basically that the difference in internal energy between steam and the person is larger than the difference between hot water and the person itself, because steam will also have latent heat of vaporization. So because of that latent heat of vaporization itself, you will it is more likely, or sorry, that steam can actually lose more heat and actually cause the person to gain more heat. There will be a higher, faster change in temperature. You will actually be likely to scald yourself and burn yourself if you are in contact with steam. That's why for normal Asian households itself, if you're eating rice and you open the rice cooker, let the steam escape first before you scoop the rice. Because if you were to put your face directly where the steam is, you can actually burn or melt your skin off. It's actually very, very dangerous. Don't joke around with this. It is something very dangerous itself. Okay? So do take note, there's a lot more applications for this, but basically we have covered the basics. So you can actually attempt the workbook to double check whether you fully understood this chapter or not. Okay?